So good afternoon, everyone. My name is Aydar Akçurin. Welcome and thank you very much for being with us today. This session is organized by TriboNet and it's the second seminar in the series. And today I'm pleased to announce that we have with us Dr. Marian. The topic of the seminar is the prediction of elastohydrodynamic film thickness parameters by machine learning approaches. A quick agenda for today. So we have around 30 to 35 minutes for the presentation and following by a question and answer session. We have quite some participants today. So during the talk, the microphones will be muted to make it easier for the presenter. And you can write your questions to the chat during the presentation, and afterwards during the Q&A session, they will be addressed. I will start by introducing Dr. Marian for those who may not know him yet. Dr. Marian is an assistant professor for multi-scale engineering mechanics at the Department of Mechanical and Metallurgical Engineering of Catholic University of Chile. His research focuses on energy efficiency and sustainability through tribology, with an emphasis on the modification of surfaces through microtexturing and coatings. Besides machine elements and engine components, he expanded his fields towards biotribology and artificial joints, as well as triboelectric nanogenerators. His research is particularly related to the development of numerical multi-scale tribosimulation and machine learning approaches. He has published more than 35 peer-reviewed publications in reputed journals and has been awarded with various individual distinctions as well as best paper awards. Furthermore, he is in the editorial boards from several journals, including Frontiers in Chemistry and Nanoscience, Industrial Lubrication and Tribology, Lubricants, as well as Tribology, Materials, Surfaces, and Interfaces journals. And Dr. Marian is a member of the Society of Tribology and Lubrication Engineers and the German Society for Tribology. And with this, without further ado, Max, the floor is yours, and I'm looking forward for your talk.
Yeah, thank you, Aydar, for the introducing words. And hello, everyone. I hope you're all doing great. And first of all, I'd like to thank you all for switching on this webinar today. And yeah, special thanks to all of the TriboNet team for inviting me to speak today about elastohydrodynamic contacts and how we might predict the behavior by machine learning approaches. So before we get into any detail, let's start with the big picture and why we would want to predict the behavior of mentioned contact types. According to Holmberg and Erdemir, around 23% of the world's energy consumption originates from tribo contacts. Of that, about 20% is used to overcome friction and roughly 3% to remanufacture worn parts. To get a better idea of what these 23% mean, let me express this in an energetic way. This corresponds to annual losses of 119 exajoule per year. An exa, that's a 1 with 19 zeros. Okay, I don't know about you, but I'm having a hard time imagining what this actually means. But maybe this can help out. 1 exajoule corresponds to the energy of an asteroid in the size of the Egyptian Cheops pyramid hitting Earth with 20 kilometers per second. So we're losing this energy 190 times a year, only due to friction and wear in tribal contacts. Now that, for me, that sounds like quite a lot, doesn't it? However, by understanding tribotechnical systems and developing new concepts, lubricants, materials, or surface technologies, we might substantially reduce friction and wear in various applications in vehicles, machinery, and other equipment. This covers manifold applications such as brakes, clutches, piston cylinder liners, journal bearings, gears, cam followers, rolling bearings, or even load bearing implants. And within all these mentioned applications, we can break down the essential contact pairings or the contact geometries of the contacting bodies into parallel or conformal contacts as well as in concentrated contacts, for which we can distinguish between line and point or elliptical contacts. The use of a lubricant is an effective way in nature and many technological applications to reduce friction and wear in highly stressed tribo contacts due to the partial separation or the complete separation of the contacting partners by an intermediate medium with low shear resistance. The formation of the separating hydrodynamic film depends on the gap geometry, the relative movement of the surfaces, the viscous lubricant medium, and adhesion conditions. So if the lubricant is drawn into the contact zone, hydrodynamic pressure can build up and thus the surfaces can be separated. In case of more heavily loaded and concentrated contacts, as we have them in rolling bearings shown here in this animation, elastic deformation of the contact partners occur due to concentrated contact geometry, and this can basically be described by the Hertzsprung theory. And due to a lubricant, there's also superimposed formation of hydrodynamic pressure. And basically in the area of the contact inlet, we have an earlier pressure rise compared to the Hertzsprung solution due to lubricant compression. And we have an almost parallel film height in a wide area of the contact, but we have an additional constriction in the film height and an additional hydrodynamic pressure spike near the outlet. And typically for EHL contacts, the lubricant film thickness and the elastic deformation are of a similar order of magnitude. Of course, the hydrodynamic pressure and fluid film formation also depend on the stress collective. So basically, the resulting pressure and lubricant gap distribution is determined by geometries of the contacting bodies, namely the radii R, for which we can calculate an equivalent radius. Of course, the material properties, especially Young's modulus and Poisson's ratio, for which we can calculate an equivalent Young's modulus. Of course, also the kinematics, namely the velocities of the components, for which we can calculate some characteristics values like the hydrodynamically effective lubricant velocity or the slide to roll ratio. And of course, finally, we have an influence of the lubricant properties, namely the viscosity eta or the density rho of the lubricant. Depending on the operating conditions as well as the involved materials and lubricants, different effects can dominate in the contact behavior, whereas elastic effects and or the piezo viscosity of the lubricant might play a role. The latter is the increase in viscosity of the lubricant under pressure, and using the dimensional parameters from Johnson, an elasticity and a viscosity parameter, we can differentiate between different regimes for EHL contacts, namely the isoviscous rigid regime, the isoviscous elastic regime, the piezoviscous rigid regime, and the piezoviscous elastic regime. So in the following, I would like to briefly introduce two conventional ways to numerically model such EHL contacts. And I will introduce two analytically solvable proximity equations. The main part will focus then on machine learning approaches to predict EHL film thickness, which was done in international collaboration with the University of Erlangen in Germany, Universidad de Sao Paulo, and the Universidad de Chile. And I will finalize this webinar with a short summary of our main findings. Okay, so generally the simulation of EHL involves various physical domains ranging from lubricant hydrodynamics over contact mechanics, potentially thermodynamics, and fluid rheology. So if we neglect the non-Newtonian and thermal effects, as well as mixed lubrication, on which I won't put any focus within this webinar, then we require both a solution of the hydrodynamic and the elastic deformation. And if flow and structural mechanics interact with each other, this is usually generally referred to as fluid structure interaction. And since both solutions influence each other, a suitable coupling is required. One way of coupling would be to perform a solution of the hydrodynamics followed by a solution of the deformation due to the pressure. So this is called a so-called weak coupling. If this step is performed only once, we speak of a unidirectional weak coupling. and it's like the most simple approach, and the interaction between fluid and structure is not sufficiently considered. In weak coupling, therefore, two steps are usually repeated sequentially until a defined convergence criterion is reached. The strong coupling, on the other hand, solves the two discretized differential equations in one joint algebraic system of equations. Generally, it is possible to use the full Navier-Stokes equations to solve EHL contact problems. In this case, however, we have to mesh the lubricant in gap height direction, which makes normalization and mesh transformation a bit more difficult, and instabilities might occur due to an over-response of the elastic deformation due to surface pressure. Therefore, the hydrodynamics is most frequently represented in the form of the so-called Reynolds differential equation. In the past, both weak and strong coupling have been used by various researchers to solve EHL problems. The former, in the form of sequential solution, represents both the first implemented and the most widely used coupling. The first work used the so-called inverse iterative method. Here the Reynolds equation is solved for the lubricant gap for a given pressure, and thereby the half-space approach is usually used to compute the elastic deformation. Second, we have so-called direct methods, which solve the Reynolds equation for the pressure, and multi-grid MG accelerated the calculation and the introduction of so-called multi-level multi-integration MLMI methods and relaxation procedures allowed to calculate higher pressures. In this context, we also have to mention the names of Van and Lubric, of course, who did some pioneering work in that direction. The weak coupled solutions are contrasted by those with a strong coupling and a simultaneous solution of the equations. However, the half-space model to use for elastic deformation results in a fully filled matrix in a nonlinear system of equations to be solved. So all mesh points basically are related to each other by integral equation, which requires quite a lot of memory and computational effort. This was allowed to be one of the main reasons why in the past mainly weak coupling solutions prevailed. But in order to obtain a sparse matrix, lower computational efforts and memory requirements, Haphi proposed to replace the elastic deformation by a FEM finite element formulation, and also to discretize the Reynolds equation with a finite element approach. Due to the strong coupling, a very good convergence behavior of the solution is achieved, which means comparatively small number of iterations to the solution, and furthermore, commercial software algorithms can be used to solve EHL contacts with the full system approach. Still, EHL simulations are rather complex and computationally expensive. For sufficiently accurate and computational efficient incorporation of EHL effects in higher level multi-body or dynamic simulations, usually analytically solvable approximating equations are used to estimate like integral fluid film parameters like the minimum or the central film thickness. So to generalize EHL calculations and the results, basically non-dimensional similarity groups were introduced by Dawson and Higginson already quite some time ago, and they proposed curve-fitted regression formulas, which from now on I will refer to as proximity equations, that basically relate those parameters from numerical simulation results. And just to make it a bit more complete, Block and Mouse later proved that these 4 parameters could be transformed into 3 independent parameters, thus introducing a low viscosity and film thickness parameter. So to estimate the minimum lubricant film thickness in an EHL infinite 2D line contact, Dawson and Higginson proposed an analytically solvable regression equation as a function of velocity, material, and load parameter. And with time, based upon more advanced isothermal EHL simulations, these parameters have been modified and extended by various authors to also cover the central film thickness or the central and minimum film thickness in point or even elliptical contacts. So basically, these are kind of polynomial regression equations to estimate film thickness parameters. As I said, there have been many more variants developed and published over time, also correction factors to cover more and more effects. And basically, they have been extended to cover a wider range of validity and also be valid in for example, isoviscous or the rigid regimes we saw earlier. So 2 years ago, we published a review article where you can find much more information on that. Therefore, I won't go into much more detail. However, already there we hypothesized that machine learning approaches could also be used for film thickness prediction, as they might have advantages compared to more complex EHL models, and also to proximity equation in terms of speed and flexibility and accuracy. So what is machine learning? Basically, machine learning, ML, and artificial intelligence are rising stars in many scientific disciplines and in industries, and high hopes are being pinned upon them. Basically, machine learning is a subdomain of artificial intelligence, and they are formed by logic, probability theory, algorithm theory, and computing. In the first step, ML involves designing computer systems for special tasks that learn from training data and over time develop and refine experience-based models that predict any kind of outcomes. So the system can thus be used to answer questions in the given field. And there are a number of different algorithms that can be used for machine learning, whereby the suitability of the algorithm is kind of task dependent. Generally, they can be categorized into supervised, unsupervised, and reinforcement learning. For supervised algorithms, they learn a relation from a given set of input and output data vectors, and during learning, a teacher or an expert provides the correct inputs and outputs. And yeah, in unsupervised learning, the algorithm generates like a statistical model that describes the given data without the model being evaluated by a teacher. Yeah, basically, I won't go into much more detail on this. Basically, what we employed later was supervised learning. But it should be said that the classification, while the classification into these three upper categories is common and widely accepted, there is no consensus on which algorithm should be assigned to which category. And so on this slide, you can see one possible allocation, but in different literature will display different classifications. Anyways, the intended usage and the numerical algorithms are manifold, ranging from support vector machines, decision trees, rule-based learners, genetic algorithms, neural networks, and so on. And various machine learning approaches have also found their way into tribology, where they can support sorting through the complexity of patterns and identifying trends within like multiple interacting features and processes. And as can easily be seen in a recent article collection and in a respective review article on current trends and applications we published in the journal Lubricants, there's a rapidly increasing number of published research that aims at monitoring and controlling, designing and optimizing, analyzing and predicting tribal systems on different scales in different areas, ranging from lubricants, drive technology, composite materials, manufacturing to surface engineering. And basically, they also employ different kind of databases, let it be experimental, numerical, or even literature-based databases. So the general idea of what I want to present in the following was to train machine learning approaches to predict lubricant film parameters in EHL context as a function of like standard input variables, as is also basically the idea of the well-known proximity equations. So in this context, the work was based on the hypothesis that ML approaches can predict relevant EHL film parameters, such as the central and the minimum lubricant gap in 2D or 3D line and 3D circular point contacts more efficiently than more complex EHL simulation models, and with high accuracy and more flexibility than analytically solvable proximity equations based upon the non-dimensional groups. In our study, we addressed the following research questions. First was, how accurate are the prediction of ML? In our case, we had a look at support vector machines, Gaussian process regression, and artificial neural networks. The latter we can see on the left-hand side. I'll go into a bit more detail in a bit. And like, how accurate are they compared to the established analytically solvable proximity equation? The second research question was, what is the influence of the training data? If we use like only the non-dimensional groups as input data instead of the original input we see on the left-hand side of the slide. Third, how do the artificial neural network architecture and structure affect the prediction quality? Fourth, what is the influence of the size of the database? And fifth, is it possible to determine locally resolved lubricant film thickness distribution, namely the lubricant gap as a function of the contact length instead of just like integral parameters like central or minimum film thickness? So the overall approach is illustrated on this slide. At first, we defined the data we need, including the original input parameters, the non-dimensional parameters from the ligand, as well as the most parameters. Subsequently, we conducted a design of experiments based upon Latin hypercube sampling and calculated all the trial points by finite element method-based EHL model, and also using the proximity equations, of course, that we have seen on the slides before. Afterwards, we split the data into training data, which was used to build a support vector machine, Gaussian process regression, as well as artificial neural networks, and into test data, which we used to evaluate the prediction quality of the ML methods, where as a criterion we use the coefficient of determination R². On this slide shows the parameters that were varied within the given boundary conditions for 2D line contact as well as a 3D point contact. I won't go into all the details on the boundaries of what we studied, but basically these parameters were sampled using a Latin hypercube sampling, and we had 1,500 trial points for the 2D line contact and 1,000 trial points for the 3D point contact. Moreover, we investigated the case for the 2D case, to what extent a reduced database how it would affect the results, and we also trained the models only with 600, 300, and 100 data points, and had a look at what does it with our prediction accuracy. And at first, we trained the models with the original EHL contact parameters or original input, but we also calculated the non-dimensional parameters GUW as well as the most parameters ML, and had a look at what does it, or how is the prediction accuracy if we train the models only with these parameters instead of the 12 we have above. So the database was then created using an EHL simulation model based upon the finite element method based full system approach from Habchi and co-workers. On the left, you can see basically the flow chart, and on the right-hand side, the solution domains. So this is the solution domain for the infinite 2D line contact, and this is for the 3D point contact, also making use of a symmetry boundary condition. So at first, the model is initialized using values from the Hodgson theory, and subsequently the initial pressure and elastic deformation is calculated for dry conditions without hydrodynamics to preset the wall system, and then the system of or the EHL problem is computed fully coupled, whereas the Reynolds equation is solved in a weak form on the boundary of the elastic body. The wall model was implemented in COMSOL multiphysics, which is also kind of state of the art now. So nothing special about the model here. And results from the calculation might look like this. So here we see, for example, the lubricant gap and the pressure distribution over the contact length for different most parameter combinations. So here we have on the x-axis the load parameter M and the viscosity parameter L. And we can see that we have different influence or different role of hydrodynamic and or elastic effects, which are more or less dominant depending on the contact conditions. So then various machine learning regression methods, including support vector machines, Gaussian process regression, and artificial neural networks were employed. All the input and the output data they were normalized on values between -1 and 1. And basically the models were developed using training data to provide like the best possible prediction for any unknown test data. And therefore we split the data set into 85% training and 50% testing data. So in detail, a linear epsilon incentive SVM was employed. Thereby the SVM represents an object set by a vector within a vector space, and hyperplanes within the space are used to separate the data points, and kernel function are then used to transform the vector space in any higher dimensional space so that interlaced vectors groups are linearly separable. The Gaussian process regression non-parametric probabilistic model was implemented, which explains the response by latent variables from a Gaussian process and explicit base functions. And finally, a multi-hidden layer feed-forward backpropagation ANN was trained utilizing the Levenberg-Marquardt algorithm. Here we can see the architecture of an ANN. Basically, they're inspired by natural brains architecture, involve a number of simple but highly interconnected information processing elements, the so-called neurons, which you can see on the bottom here. And yeah, basically transfer and propagation functions determine the neuron's network input based on output weighting, and the calculation of the output basically is achieved by activation functions considering a threshold value. And during training of the ANN, the weightings and the thresholds are adjusted to optimize the overall prediction quality. But as you might guess, the topology and the architecture of this ANN, like how many neurons are arranged in how many of the hidden layers in between the input and the output layer. So this architecture needs to be tailored for the respective application. Okay, so now let's check out some results. We start with the prediction from SVM and GPR. There's a lot going on the slide, but I'll try to guide you through this. In the table on the top, we can see the R-square values against the testing data, and in the graphs on the bottom, we can see the predicted versus the predicted values from the ML versus the calculated values from the EHL model. And basically, the closer the R-square value to 1, as well as the more closely the data points are on this 45-degree line, the better the prediction accuracy. And we can see that basically the prediction accuracy or the EHL simulation results were quite accurately predicted by both the SVM and the GPR methods. And we have our square value larger than 0.99, which is quite good. And they were also partly higher than the R-square values of analytically solvable proximity equations. So we had quite good prediction accuracy. And when we compare the SVM with the GPR proved to be slightly superior to SVM. For aforementioned results, we used the original input data to train the ML algorithms, but when we use, instead of the original inputs, we use the non-dimensional parameters UGW or ML, this resulted in significantly lower accuracy or like total insufficient prediction accuracy. So basically the prediction partly were totally off. The R-square values fell well below 0.9 or partly almost to 0. And this, we think that this substantially inferior prediction quality can be traced back to redundant input variables from different original input data. So that basically it is possible that that similar dimensionless variables can lead to different film thickness parameters or different dimensional film thickness parameters. And this inconsistency in the database led to problems when training the SVM and in particular the GPR models. On this slide, we can see some results for the neural networks. Again, the R-square values for prediction. This is for prediction of the 3D circular point contact for the central and the minimum film thickness. And we can see different prediction accuracy for different architecture or topology of the neural networks with a different number of neurons per hidden layer, which we write between 10 and 20, as well as a different number of hidden layers, which we will write between 1 and 3. Again, here the original input values of the EHL simulation were used for training. And we can see that the EHL film parameters were predicted also with quite high accuracy. R-square values way above 0.99, at least by some ANN configurations. This also went to even up to 1. We saw that the number of neurons per hidden layer played a less dominant role compared to the number of hidden layers. Basically, we got quite good prediction accuracy when we had more than 10 neurons per hidden layer, and we saw that the best prediction accuracy we obtained for 2 hidden layers, followed by 3, and then only 1 hidden layer. So basically, for all the rest of the investigation, we decided to stick with this configuration of 12 neurons in 2 hidden layers. And basically, we can also see the results for this configuration on the bottom, the comparison of the predicted value by the ML model versus the calculated values from the EHL simulation. Here we can see that basically the 3D point contact featured better accuracy compared to the 2D line contact, which may be due to the larger database we had for the 2D line contact, and thus to some kind of overfitting of the model, which then was reflected in an inferior prediction accuracy against the testing data. But I'll show you a bit more on that shortly. So similar to SVM and GPR, training the ANN with dimensionless parameters with UGW and ML resulted in a considerable reduction of the prediction quality due to also to inconsistencies in the training data set. We further varied the activation function of the neural network. So this still is an ANN with 12 neurons in each of the 2 hidden layers. And we trained it with a hyperbolic tangent, as in the case before, with a sigmoid logistic and a linear identity activation function. So please note that the output and the propagation functions were still kept constant, and only the activation function was right. And here we saw that basically the sigmoid and the hyperbolic tangent function both led to high R-square values, well beyond 0.99, while the linear identity function resulted in a slightly downgraded prediction accuracy. So to minimize the efforts that we require to generate the database and train the models, it is a good approach to keep the number of training data as small as possible without affecting the prediction quality. And here we can see the R-square values. This is for the infinite 2D line contact with a varying number of input data. And even if the original data or training data was reduced to 600 data points, which is less than half of what we had initially, the R-square values were quite high at a level above 0.99, and here we're even like 1.0. And so basically this was even better than we had for the larger database. So this implied that for the larger training database with more than 1,000 data points, we had some overfitting of the model. But we saw that for lower number of training data sets like 300 or 100, the coefficients of determinations showed a decreasing tendency, but still stayed above 0.9, which is quite nice even for a small amount of data. So we can also see this on this plot where the predicted value versus the calculated value. So we have a quite nice fit for training with 600 data set, and the scatter becomes a lot larger for training with only 100 data points. So for us, for the present case where we had like 12 input variables that were right, the training data set with 600 points proved to be quite sufficient. One last aspect I would like to show you is the prediction of local lubricant gap distribution. This is for an infinite 2D line contact. And basically there we use the local film thickness, in other words, the film thickness and the film thickness and the contact length parameter X, we use both as the training data to train the ANN model, also with the same configuration that I mentioned before. And thereby we reached an overall square value of 1.0 against testing data, including all data sets and positions along the contact length. And this quite nice prediction accuracy can also be seen from on this slide from the direct comparison of the lubricant gap from when calculated with the FEM-based EHL simulation as well as the ANN prediction. So basically, we had a quite good agreement in most of the part of the contact length, also in the minimum film thickness, and we had only had a slight overshooting here in the area directly in front of the minimum film thickness. And to compare the execution time of the FEM simulation and the ANN, we calculated the lubricant film thickness for a data set that was not included in the training data, using both methods on the same computer and with, I got to say, with the same discretization. Basically, it would be possible to query any discretization with the INN that is desired. And thereby the ANN was over 25 times faster than the FEM model. And yeah, with less than a second, the calculation time is probably comparable to that when we solve analytically solvable proximity equations in any kind of programming language. But the ANN offers the possibility not only to predict central and minimum film thickness, but also the distribution along the contact length. And we think that when we incorporate ANNs into multi-body system simulations or dynamic simulations, we think that the accuracy in friction and dynamic analysis or the identification of critical operating conditions could become even more precise without at all negatively affecting the required computational time. So this is what we found quite interesting, that this was possible to predict. So this brings me almost to the end of this webinar, and I'll just wrap things up really quickly by answering the research questions that are raised during my talk. First, I've shown you that ML approaches can indeed predict relevant film thickness parameters more efficiently than proximity equations in terms of accuracy and flexibility. Secondly, in contrast to proximity equations, the usage of original EHL input data is quite crucial for the ML approaches, and only using the dimensionless parameters for training notably decreased the prediction accuracy. Third, the architecture of an ANN, especially the number of hidden layers and the number of neurons in each of the hidden layers, notably influences the prediction accuracy. So this has to be designed very well. And for the data set we studied within, or that I presented today, we found that ANNs with 12 neurons in each of 2 hidden layers, as well as hyperbolic tangent or sigmoid activation functions, were most favorable. Fourth, I showed you that the size of the database also affects the prediction quality, and for our study, the ML approaches trained using 12 input parameters, roughly 600 training data proved to be sufficient to reach high R-square values without getting into overfitting. And fifth, last but not least, in addition to global parameters like the minimum film thickness, ML approaches can also predict the local lubricant film thickness distribution. And at present, lubrication behavior and dynamic calculations in multi-body system simulations typically employ these analytically solvable equations and the Hertzen theory to account for fluid film formation and pressure distribution. And we think that in the future, the incorporation of ML approaches such as ANNs into these higher level simulations will add value to engineering system design processes. So that shall be all from my side for now. Again, thank you very much for having me on this TriboNet webinar, and thanks to every single one of you in the audience for attending today. Really appreciate it. If you're interested, you can also find all the detailed information in our recent paper published Open Access and Friction. But I'm also more than happy to try to answer any questions that might pop up now. So thank you all.
Thank you very much, Max, for the great talk. It's very interesting. I'm very impressed with the accuracy of the prediction of the whole film thickness. Actually, I think it can be used, can be very helpful.
Yes, that's also what we thought, that this was one of the most surprising and most exciting things to predict locally.
Yeah. So maybe it's good now to go through the questions, if there are any in the chats. Okay, I see. Yeah, I see there are. Guys, if you have any questions, you could ask, and you can type in. And in the meantime, maybe I can ask a couple of questions. So this film thickness prediction in the contact. Is it for line contacts only, or is it also available for point contacts?
So you're referring to the local film thickness distribution?
Yeah.
So far we only did it for the line contact because it's quite a lot of data to handle. But basically, it should not have any influence. Basically, what you do is you add to your the 12 input parameters that we had before that you also put into the EHL simulation. You take this as an input, and also the variable x, and could also be potentially y, the Cartesian coordinate system. So basically, you just have a lot more input data to train your models. But of course, this would not be the problem, because we have to distinguish between training time and execution time, and so the training time does not really matter a lot because it is done once, and then we have a very short execution time. And so I believe that it is quite possible. At the moment, we are working into that direction to also have a 3D film thickness distribution prediction with the ANN, maybe for point or for elliptical contacts as well. And we also want to incorporate more complex effects, it's feasible to also include thermal properties and thermal effects, other rheological models to account for shear thinning, maybe surface roughness and so on. So there's a lot that might be possible to predict while keeping computational time quite short.
Yeah, of course, in this 3D case, there's a difference between the computational times is going to be is even greater.
Yes, I also think, because the computational time from the FVM approach for a 3D case to the 2D case, it's also quite there's quite some difference. I don't think there will be such a difference in between when you execute the already trained neural network, for example, to just basically you just query data. You say, okay, I want the distribution in this case X and Y. You get the results. Then you just run through it and you have it.
We have guys. We have a lot of questions coming in. This is
okay. Let's go through them then.
First of all, either could you unmute Vasim Hapche, because
unmute. Sure.
It's a kind of a long question.
That's if I can do, of course.
Meanwhile, did you manage, or otherwise we jump to the second one while you work on that?
Yeah.
Okay, so the next question, or the second question, is from Rafael Vilmer Contreras Urguiles. In the case that the surfaces are in counter-rotating, is there any revision of the state of the art? How would be the process of film thickness prediction?
Basically in the case that, if I understood the question right, if they're like counter-rotating with like basically different directions of the velocities.
I understand the same.
Okay. Basically, it will be quite the same as long as you have some kind of hydrodynamically effective velocity. Basically, this is what goes into your simulation results. And in this case, of course, we did not consider, because we used an isothermal model without any shear thinning effects to train it, and it was the first pilot study and approach to tackle this issue. And basically the velocity differences of the counterparts did not really play a role. Basically, what goes in is the effective velocity.
So it could be negative or positive, but that's it. Yeah.
Yes, I hope that answered the question.
Cool, thank you. Either did you manage?
Yes, I'm muted. Well, I mean, I allowed Wasim to use the mic, but he has to then unmute and check. So Wasim,
yeah, thank you. I don't know if you can hear me.
Yes,
we can hear you. Clear.
Okay, great. Well, I managed to type it in the end, but it's better if I can interact directly with Max. Max, thank you very much for this really interesting presentation. I enjoyed reading the paper fully, but I even enjoyed looking at your presentation today. So my question is related to the fact that you showed on slide 19 and 21, I guess. You showed that the machine learning approach fails when you try to predict film thicknesses from dimensionless parameters like the UGW or the ML parameters. And in my opinion, this failure comes from the fact that these parameters were designed to predict dimensionless film thicknesses. And what you're trying to do is you are trying to predict dimensional film thicknesses from these dimensional parameters. And I guess if you try to just predict dimensionless film thicknesses from these parameters, you would get a much more accurate prediction than what you're getting right now. So I was wondering if you tried that and if you have any thoughts on this.
Thank you, Wasim. First of all, thanks for attending. Really appreciate it, and thanks for the nice feedback. No, you're absolutely right. Basically, we just tried to predict a dimensional film thickness from non-dimensional parameters, and I believe that the prediction accuracy would increase if we also predict the dimensionless film thickness, which is kind of normalized on the radius of the contact. So basically, yeah, that's indeed an issue. That's a good point. We're currently trying that out. We have not any definitive results on it yet, but we're currently doing that and running some tests on that direction. But yes, I also suppose it should be possible, because right now we have as I mentioned, the inconsistency, because you can get different dimensional film thickness from similar non-dimensional parameters, and this should no longer be the case if we predict the dimensionless film thickness.
Okay, great. Thank you.
Cool. Actually, we are getting a lot of questions. So, Max, you were really successful there. Or not.
Or not, yeah.
I can see the next one in line is from Stephen Boucher. The question is, he thanks you for the presentation, but how does the ML approach compare with the analytic equations considering computational intensity of simulation?
Well, basically, this is kind of kind of tricky to answer because it probably depends very much also on the programming language where you implement it. So all the machine learning approaches we tried out, we implemented them in method MATLAB, which might also not be the most efficient programming language. So I think you can get even better computational time if you go into other languages. And so it depends, because for example, for the non-dimensional parameters and the proximity equations, you can just solve them in by hand with a calculator in Excel or in any kind of software you want. Basically, it's just like simple analytical tasks. So it's a bit difficult to compare, especially like if you can implement it in different software. But still, I believe that to query these simple integral parameters, we're quite comparable when we're solving it in the same programming language. And yeah, you can still get a lot more out from a lot more information from the ML model.
Okay, could you comment really quick about the effort that is required to generate the original training set?
Yeah, well, on this slide we have the computational time. This was for the 2D line contact for the FEM-based EHL simulation. So this was 19 seconds. And when we had the original data set of 1,500 or like the reduced one of 600, you can just multiply it, and then of course you can parallelize it. But actually it was not that much of a computational effort. And to generate the database and subsequently to train the machine learning approaches was in the range of a couple of minutes to train them. So it's not overly computational expensive actually. So the training of the ML would be a couple of minutes, and then the execution time less than a second.
So we have a lot of questions, and I think that the best would be that we really send them to you afterwards, so you can then directly get in contact. So I'm sorry if I'm missing some, because it's difficult for me to prioritize now, because it's really, for example, yes, some of them are really specific. Okay, so Francisco Franco Martinez. Hello, Max. Thank you for the talk. I have two questions about the artificial neural network. Why did you use the hyperbolic and tangent hyperbolic and sigmoid as activation functions? That's the first question. And the second one is, what is the loss function you use for the ANN?
Pardon, I didn't get the last part of the question, I think.
Sorry, the second part is, what is the loss function you used for the ANN, or artificial neural network?
Okay. Yeah, so basically, yeah, I mean, you can also, we've also published all the details you need to reproduce the results in the paper. Basically, we used the hyperbolic and the sigmoid function because they're quite common used activation functions, and they are quite nicely implemented in methods MATLAB, so it's quite easy, it's quite straightforward to use. And yeah, in the beginning we only used the hyperbolic tangent function, and then we tried out to several other activation functions, but basically yeah, we saw that it does not really that much affect the prediction accuracy, or if you account for some kind of nonlinear impact. So only basically the linear identity function was basically, or led to a downgraded behavior of the prediction accuracy when we use the linear identity for activation functions. And yeah, for the last to function the equation function through the output layer, we used a linear function, which is quite state of the art as well. It's quite common to do so.
Okay, and I think that the first question that about the counter rotating surfaces, maybe I think I misinterpreted, because there's also Anurag Singh that has the same question. Would you mind either unmuting them? Because maybe it would be easier if we have like 4 minutes. So I think it's good.
Who do you want me to unmute? I'm sorry.
Or Anurag Singh or Rafael Vilmer Contreras Urguiles, because I think that we didn't get it.
Anurag, I unmuted you, so if you could unmute yourself.
Hi, yes, this is Anurag. Thank you
Hi.
for the presentation. Yeah, so I wanted to just ask, I think someone also asked the same question, that if you are trying to predict the analytical film EHL, if you use the analytical model like Dawson and Hamrock, it predicts zero film formation if the surfaces are moving counter, like their direction is opposite. Is there any way you can use these models to predict EHL film using the ANN or something, or is it like ever tried? Yeah, I'm just please go ahead.
Yeah, thanks for your question. Yeah, basically, as I said, the input parameters are just like the velocities of the surfaces, and basically it does not really matter if it's negative. Basically, because what really matters is the hydrodynamic effective velocity, and like it doesn't really matter in which direction the contact goes. So basically, we get a prediction result. Related to like going down to zero, of course, we have to emphasize that like you can only trust the ANN within the frame that you covered by the training data set. And theoretically, it would also, for example, be possible that because it's not a physical solution, or basically it would be possible that you end up with a prediction of a negative film thickness. We did not encounter that because we did not cover it. We always stayed like in the full film regime, and we did not encounter this kind of problem. But I guess you could like account for it with any kind of simple simple boundary conditions as well, to keep it above zero. Like if you had zero velocity, for example, where you just go to zero. I hope that kind of answered the question now.
Yeah, sure. Thanks.
Good. We have time to squeeze a very last question, and I think it's an interesting one from Michael Paul. Is I don't have training data, but I do have the need to predict film thickness. I think I'm in the same position.
I can relate to that, right?
Yeah. Is it possible to use this method?
Yeah, basically we could provide the trained ANN models, for example, if you just get in touch with me. But there are a lot of film thickness calculators also online which you can use, and some approaches to quite easily implement some first EHL models also. I mean, we have with Wasim Habshi in the audience, who brought a very nice book how to implement the EHL model in the full system approach, and basically it's quite straightforward to have a first simple model that we also used to train these machine learning algorithms. Anyways, I guess the more interesting part, or the really exciting part, is now to come to in what we're working right now towards, like incorporating more and more effects by the ML approaches, and like to generate a more even greater database that we need, because like we have a lot more input variables if we take into account, I don't know, shear thinning, thermal effects, and all these kind of stuff. So we need probably still a larger database. But coming back to your question, we can provide you with the trained ANN if you just write me an email. That should be no problem.
That sounds good.
Yeah, due to time, guys, I guess it's time to finalize. There are still more questions. So I think you know, what we can do is that we will publish the recording of the video on TriboNet and on the webinar section, and you can actually write down the comments there, and I hope Max can address them, or you, of course, can contact Max directly. Our next seminar is planned for September with Professor Rob Karpik as a speaker. So I invite you guys to sign up to the newsletter if you have not done so yet. And I hope you guys enjoyed the seminar as well as I did. And I would like to thank you, Max, again for this great presentation and for the discussion. I wish you all the luck with your future work, which I will be then looking forward to. And thank you for participating, all the people today. And I wish you all a good weekend. Yes.
Yeah, thank you all from my side as well.
Thank you. Bye, guys.
Thanks a lot. Have a good day. Bye.
Have a good night.